This episode of the Pumps and Systems podcast is brought to you by SEPCO, fluid sealing solutions for every application.
When people don't follow procedures, it's not because they don't want to. Most people want to come in and provide great services, do a great job. When they don't follow a procedure, there's usually a reason why.
Hello and welcome to the Pumps and Systems podcast. I am your host, Tom Baer, a managing editor at Pumps and Systems magazine. Today, we're going to be speaking with Chris Tyndall, regional manager from SEPCO, who's going to tell us all about condition-based maintenance strategies and how they can be used to improve mechanical seal reliability. So without any further ado, let's get into the episode. And let me officially welcome you to the Pumps and Systems podcast. And thanks for taking the time to talk with us. So how are you doing today?
I'm doing great, Tom. Thank you.
That's
Thanks
good.
for
Yeah,
having me.
sure thing. All right. So today we're going to be talking about condition-based maintenance and mechanical seals. But before we get into that, would you mind introducing yourself? So tell us a little about who you are, where you work, anything you think that our listeners and viewers might want to know.
So my name is Chris Tyndall. I'm regional products manager for SEPCO, covering the South Central U.S. region. I've been working in and around maintenance and reliability programs over the last 30 years. Began in inside plants, chemical plants, and refineries, and spent about a third of my career doing that before moving into consulting services, and spent a good portion doing that, and then transitioned into products and support products. Main focus during that time has been around condition monitoring technologies. So using technologies to develop condition-based maintenance programs for rotating assets. I joined SEPCO, Sealing Equipment Products Company, in 2016 and had an opportunity to switch from the services side of the industry to more of focus on product solutions. And SEPCO is a domestic manufacturer. We make engineered fluid sealing products and performance polymers like mechanical seals, packing, gaskets. And we also manufacture high temperature and abrasion resistant products for the aerospace industry. You know, as a regional products manager, my job is to support our OEM customers and distribution partners. I thought I would be narrowing down my focus to fluid sealing products. But what I've found is I have plenty of opportunity to go back to my roots in condition monitoring. So I think, one of the things that kind of sparked this conversation that we're having is the fact that, fluid sealing products, mechanical seal in particular, is considered by a lot of people in the fluid sealing industry as a original condition monitoring device, and meaning that the seal acts as a fuse in the system and it will pop, they say, as mechanical conditions change in a pump. And so something I've learned over the last 8 years working in this industry is that the condition monitoring technologies that I used to previously had used to focus on monitoring bearing condition, it can be adjusted to provide early precursor warnings for identifying premature seal failures and failures in seal systems. And I think that's more importantly, I see a trend in the industry where people are starting to realize that, and they're applying condition monitoring technologies to the support systems, more importantly, that maintain the reliability of mechanical seals.
Okay, so it's a pretty far-reaching sort of thing.
It is, yes.
So you went into this a little bit, but I was going to ask you if you could, I think, because we often like to start with the absolute basics. So would you be able to tell us kind of the basics of what is condition-based maintenance? What are we talking about when we talk about condition-based maintenance from a basics kind of perspective?
Condition-based maintenance is maintenance that is done based on the condition of the machine. And so we use various technologies, starting with just basic inspection routes using our human senses, our sight, smell, hearing, and such to determine the condition of an asset. And then we have technologies such as vibration analysis, our vibration instruments, ultrasonic instruments, thermal cameras. We have motion amplification, which is really cool. I've seen that applied and had the opportunity to use that in mechanical seals. So that's something that is a current product trend in the market, newer technology over the last couple of years. And then oil analysis. Oil analysis is typically we're using that to look at bearings and look at machinery wear, look at the lubricant condition. And actually, when it comes to fluid sealing products, we rely heavily on clean, cool lubricants to maintain the seal faces. So oil analysis is something that I find that is a great opportunity to incorporate a technology into monitoring seal systems and making sure that they have the proper conditions for mechanical seals to perform and perform reliably.
So then, let's talk more about mechanical seals. So how can we apply condition-based maintenance strategies to improve mechanical seals?
That's a great question. So first, as with anything, if you cannot measure it, you cannot improve it. So we have to start with establishing a baseline to move on from. And so to do that, the best place to start is to talk to your seal manufacturer, to go to the guys that are providing your mechanical seals and have them provide you a list of the mechanical seals that are installed in your facility. And then ask them for the current mean time between failure rates for each location. With that data in hand, you can sort out the bad actors. You can begin classifying the bad actors according to their location and really start to break down the cause and failure mechanisms related to those bad actors, from that list. And so, and we have well-documented failure analysis processes and standards available that provide a reference for you to begin. A great example is ISO 14224. That's a good standard that just kind of outlines a process for classifying, to get the common language together for whatever you're going to use within your facility. We all need to speak the same language and understand what we're trying to communicate. Next is to identify seal failure mechanisms that we talked about, define the condition monitoring standards. Once you know what the failure mechanism is, then you can start looking at how is that going to show up, and what is the earliest technology? What kind of technologies or inspection processes can I put in place to identify the onset of those failure mechanisms? I said vibration, ultrasound, motion amplification. We'll talk some more about that. Temperature, pressure, flow, and then condition monitoring for the lubricants that are being used. Those can all help identify the onset of known failure mechanisms. And again, your seal manufacturer, the seal provider that you're using in your facility, they should be able to provide you or will provide you with the target threshold levels. So they have engineered these products. They know what the pressure, temperature, oil cleanliness levels need to be, and they're happy to share that information. They'll get by making sure that you have inspection PMs in place, you will extend the performance and reliability of each seal application. And really, best practice that I see in the industry is each of your mechanical seal locations should have some form of PFD or PNID that documents the required fluid sealing conditions, the temperature, the flow, the pressure, vibration levels, and oil cleanliness standards. And so, once you have all that in place, it really comes down to measuring the performance. So that's the last step. Measure the success of your plan. How is it working? We sat down and we established a plan to to monitor the assets. How is that working for you? You have that Dr. Phil moment. And so you document your successes. And more importantly, you document premature failures, any opportunities that you have to improve the system, because the best laid plans still will lead to opportunities. And so then you conduct failure analysis, determine the causes of why a failure occurred, and you adjust. So the whole plan, check, and plan, do, check, and adjust is the process. It's a basic reliability process.
That's very true. You can learn a lot from failures. So that's good that that's part of the process.
Definitely.
So then let's say that you have no baseline seal performance history and only minimal technical data. How do you get started in that kind of situation?
So what I see in the industry is that's more often than not, that's the case. People do not have that information readily available. They may have the information stored away in their CMMS filing cabinets, but for the most part, they're not tracking these components, mechanical seals. They're not able to tell you. A common problem is if you go to just pick an industry, chemical plants, refineries, manufacturing, and you ask them, what is your mean time between failure? How many mechanical seals do you have installed? What is the failure rate? They're not going to have that information readily available. The good news is your seal manufacturer, again, the distributors, the support vendors that you have providing these products should have the information, but if they don't, it's because the customer did not provide them the opportunities a lot of times. But they're generally happy to help. I mean, they want this information. That's only going to benefit their partnership with their customers. And so they'll help you walk down the assets and collect this data for you. And it benefits both parties. So like any RCM project, you have to start with a good asset list. You have to obtain information about the asset locations and what is known. What do you know about what's expected to be out there? What kind of mechanical seals, what kind of sealing products are being used? And then you have to walk down each asset and document what's actually out in the field. It's a great process to go through. Even if you think you know what you have out there, it's good to walk out and verify before you start these processes. It doesn't take long. It takes a couple of days and a couple of just qualified people to just walk down and assess, what's going on. The next step would be to run a storeroom report to find out mechanical seal part inventory. I mean, that's something that everybody will have. You will know at some level what's on the shelf. What are you actually using? And you can marry those two together. Now that you know what's in the field and you know what's in inventory, you can start associating the usage to what's being consumed by what grouping of assets, how many pumps. So you would run a seal usage report. It's good to get as far back as you can. If you can get 10 years longer, if possible, that gives you a good baseline. You conduct a storeroom survey to determine the inventory levels. At that point, you can kind of see the min maxes of what's going on. And then you can run a report. From that, you can determine the mean time between failure for the groupings. So you may have a mechanical seal that's used in 20 different locations. And so you can base that off of your seal usage. You can say those 20 locations, if we use, 10 mechanical seals a year, that's not good. If you're using 1 out of 20, then you're getting more of that's a high level mean time between failure. Another thing that we'll do with customers is the information is usually in the long description. So if you look at, for instance, every asset in a maintenance CMMS or EAM system, you'll be able to pull a work order history. And then in the description, you'll have you can run a query that basically says, find all of the work order work request descriptions that went in the system that contained something like leak or has steel as a word contained in the long description. That works really well to just filter down all of the data. So there may be thousands of entries into the CMMS, but what you're looking for is how many of those were generated because someone was out in your facility and they saw a leak or they saw a seal, seals leaking, seal failed. So those are the two common ones. There's a couple other words you can kind of throw in there to filter with. But that's a quick way to be able to just then run a per asset. How many times does that occur where the work that is being done to your asset is being generated because of a seal leak, whether it be mechanical seal or gasket. And so that's a good place to start, and once you have that baseline and you say, then you can start applying the CBM process that we just outlined.
So let's talk a little about seal failures, starting again with just the basics. So how do we define a seal failure?
Failure occurs when an asset fails to perform its design function. So an example being a pump. It's designed to move product at a certain volume, per a certain time interval. So gallons per minute at a defined pressure of, feet ahead to maintain, some operating parameter, flow, level, temperature, pressure, etc. And so the seal is a component of a pump generally and other rotating equipment. So anything where a rotating shaft will enter a non-rotating component that's used to move liquids or powders or something from point A to point B. Every time you have a rotating shaft entering a stationary component, you have to have some form of seal, whether it be packing or some static seal like a lip seal or mechanical seal, engineered sealing products. And so again, an asset failure occurs when an asset fails to perform its desired function. The mechanical seal or fluid sealing products, the function is to keep the product that's being moved in and keep contaminants out. And so when it fails to do one of those two things, whether it's sealing a gearbox and, lubrication, or it's sealing a bearing, transmission device, some kind of bearing housing, or a pump, it's it has a desired function. And when it stops performing that function, the asset may still perform. So the pump can still may necessarily or may not have failed its function. It can still provide the flow, gallons per minute at the right level, pressure, temperature. But generally, when something starts leaking, we cannot continue to let it leak. And so the seal itself then dictates the rebuild of that asset. And I think that's the biggest problem is that is driving repairs for other asset locations. The primary asset has to be pulled and reconditioned just to replace a mechanical seal that failed. So it can drive cost, even though the mechanical seal cost is much smaller and more insignificant as compared to the overall asset cost. So so that's seals. Seal failure occurs when a seal fails to perform its function.
Makes perfect sense to me. Okay. This episode of the Pumps and Systems podcast is brought to you by SEPCO. SEPCO has been a leading provider of quality products and exceptional service for over 40 years, but we're more than just a provider, we're your partner. Our products range from mechanical seals to compression packing, graphite items, and gasketing materials. Additionally, we offer specialized items like die-formed packing rings, molded PTFE parts, thermal management solutions, and fiberglass products. Find your sealing solution today at sepco.com. All right, so then what are some of the root causes of seal failures generally?
That is a term that needs to be separated from failure mechanism. So the root cause is, why did the failure mechanism start? And a lot of times there's a human element to root cause. I always think about process and procedure when it comes to cause. And really, The standard we talked about earlier, the ISO 14224, it's one of the things I like about that standard is they go back to establishing a cause. What was it? Was it design related causes? It's something in the manufacturing process or in the engineering process. When we were looking at this particular pump or asset location, and we were considering all of the factors, the physical factors that are impacting that, the environment that is being placed in, temperature, chemical, pH, the solids, the pressures that are occurring, the shaft speeds. There's a design factor, and so at the forefront, I think that's the first one that when we have failures, we need to look at was it something related to the design related causes. And so that's how we would, there's really four that you would classify. So design related causes, then fabrication and installation related causes. And so that's still, both of these rest with the manufacturer. So whoever designed and engineered this system is working in partnership with, the customer. And based on the information the customer is giving them, they design a fluid sealing product. And if there's a failure that occurs, it could be the manufacturer messed up, human error. You don't want to rule that out. I mean, manufacturers don't like talking about that, but we design things just like everyone else to try to provide a solution in the field and to fit the process. And then there could be an issue. There could be an issue with the quality. There could be an issue with the just the overall tolerances that the part was manufactured to. So I always keep that on the table. I mean, for at the forefront is design related causes and fabrication and installation related causes. The third one is causes related to operations and maintenance. Operations and maintenance. How is it operated and how is it maintained? Are we following the processes and procedures? And then failures related to management. And when I say that, management is a big part of that. What kind of management philosophy are we taking? Are we running to failure? Are we using condition-based maintenance? Are we introducing faults? Are we providing resources? Because we all have limited resources, and management has to make decisions all the time to say, hey, this is what I have to work with. I can only get so much done. So one of those four are typically the cause, and there's always miscellaneous, the oddball things, but most everything will fall into those four buckets. And really the way that works, regardless of the failure mechanism, whether it's erosion, corrosion, fatigue, overload, some kind of mechanical or chemical condition, failures at the bottom line happen for one of three reasons. Okay. Number one, there's no procedure that exists to eliminate or control the failure mechanism. So there's no procedure. So we're just kind of running and hoping for the best, to control something that maybe we know about or maybe we don't know about. But those failure mechanisms, whether you know about them or not, will do what they do. Erosion, corrosion, those things, all of those mechanical conditions will act regardless of whether we're paying attention to them or not, and that will result in a failure. Number two, you may have a procedure that exists, but we weren't following it. And that's pretty common. You'll see that you'll develop a procedure and it's not being followed. And that may be due to management. Management didn't provide the resources to do the inspection. We didn't have the resources to do the inspection. Or a great opportunity to learn is when people don't follow procedures, it's not because they don't want to. Most people want to come in and provide great services, do a great job to the highest potential. When they don't follow a procedure, there's usually a reason why. Maybe it's an ergonomic reason, maybe it's just an opportunity reason. But we develop shortcuts. Maybe it is that they don't understand why, or a lot of times people will say, well, I just don't do that anymore because nobody cares. I'm documenting the problem and nobody's responding to it. So again, those fall into two buckets. You didn't follow the procedure, so there was an operation or maintenance issue, But then underlying below that is a management issue, because perhaps management does not have it, as it's not on their radar to take care of it. They don't have the resources allocated. And then lastly, the third reason that things fail, and this can be applied to mechanical seals or anything. The third reason is procedure was followed and it didn't deliver the results that we expected. So, we'll sit down and we'll say, this is the failure mechanisms that we expect that are going to be acting upon this machine. And so we write the best procedures and we execute the best procedures that we think will help control or eliminate that failure mechanism. And it wins anyway. That happens. And as long as you keep an open mind to decide or determining what the root cause is, you can fix it. You have to admit, sometimes we are the problem. Sometimes we didn't, we made a good plan and it just didn't work. And those are the opportunities, always an opportunity. That's like you said, failures are great opportunities to improve. Without failures, we never improve. We're never pushing the limits of what's possible.
You mentioned seal failure mechanisms a few times. So would you tell us a little more about that?
People are a huge variable. I mean, reliability is basically controlling variability. You look at all the variables that are impacting your process, and then to make the process more reliable, you start addressing the variables. If you can reduce variables and control variables, your system becomes more reliable, more repeatable, right? So you're taking out all of the opportunities for it to deviate. And the great thing about failure mechanisms, I like working with machines. That's something that I think that's why I spent so much time and still kind of go back to condition monitoring, because machines always, they're predictable. Materials will always do what they do. If you apply a certain material to a temperature or pressure or a corrosive environment, it is going to react to that environment. And so the job of designing products for applications is to determine what is the environment, what can I control in that environment. So with a mechanical seal, if I can keep a mechanical seal, put a double mechanical seal with a seal support system, that mechanical seal doesn't care necessarily what's going on inside the pump. I'm taking control of the environment that those seal faces are seeing. And so I choose materials that can resist the pressures and temperatures and the chemical attacks, erosive attacks that are happening inside of the machine. And then where the seal faces, where the rotating face and the stationary face come together and need to be lubricated, I can control that environment. I can keep it cool and clean and at the right pressure to keep those seal faces separated and lubricated. And if I do that, I am maximizing the opportunity for that seal to perform in whatever environment, whether it be a clean environment or a high pressure environment where it's being attacked. And so failure mechanisms really can, I like the ISO standard. There's a lot of them out there. I still go back to erosion, corrosion, fatigue, and overload. They're subsets of that, but that's something that stuck with me for a long time. When you're doing failure analysis, you're looking at really those four cover the majority, 80%. I mean, you can argue that each one can be broken down into other subsets of, but erosion, corrosion, fatigue, and overload are what you're dealing with mechanical assets or mechanical parts. So in the standard, you've got five. You've got mechanical failure, which is related to deformation, looseness, sticking, clearances, and alignments. Failures caused by just mechanical stresses that are applied to the part or to the asset. Then there's material failures that are, the erosion, abrasive, fracturing. A material failure could be an overload, a fracture, a break, a breach. It bent. It passed its it's physical limits. There's also the third one listed in the standard is instrument failures. Failures related to faulty instrumentations. You're not getting the right information. It could be pressure flow, something that's an external force that's being applied to the machine because of an instrument failure. Electrical failures is part of the standard. That's the fourth one, just because it's, there's other systems that electrically can cause a machine to stop functioning. Even within a mechanical seal, I mean, if the power goes out, pumps stop moving, and mechanical seals can fail as a result from sudden stops, sudden starts, sudden disruptions from electrical systems. You can also have stray currents that can affect seals. You can have seal support systems that lose power, that become blocked and can't flow because of whatever circulating system. The cooler fails, and now you've got oil and water mixing, or you have a filter that's plugged and it doesn't bypass, or it bypasses and allows contaminants to get in. And then the fifth one is external influences, something outside of the design of that machine, something upstream. It could be a control valve. It can be a process that changes. Sometimes it's just a cleaning process where we decide that, hey, we're going to clean in place and we're going to use steam, or we're going to use some kind of chemical that was not discussed in the original plan. So external influences, but those are the mechanisms, things that are attacking your mechanical seal and any component for that matter.
Next, let's talk a little about post-mortem failure analysis. So how does that fit into the process?
Yeah, that's extremely important. So this is the last step. If anytime something fails, especially if it becomes a bad actor, if you're measuring performance, then you'll be able to determine your bad actors. And because we talked a lot about limited resources nowadays we're doing more with less, and so you have to focus those resources. And so using bad actors is a great way to do that, to make sure that you're putting your efforts in the right places. This is another place where the seal manufacturer and your distributor come in. They provide failure analysis. What's a common problem is there's a lot of people that don't take advantage of that aren't asking for the failure analysis and aren't tracking the results from the failure analysis. There needs to be a partnership in place. And so as part of this process, if you're going to use condition monitoring, you've established a plan, you've executed the plan, you've measured the results. And now when something comes out of service, you want to analyze why it failed. And so when it comes to engineered sealing products, you've really only got 5 components. And I love things that I can do on one hand. So you've got a gland, you've got a rotating seal, a stationary seal, you've got springs, something to load the seal faces together. One of them's spinning, one of them's stationary. And you've got static seals, you've got gaskets and O-rings. Each one of those devices are used, they're engineered together, and they're used to create a seal on the machine. So when a seal fails prematurely, what's cool about that is that each one of those tell a story. So when a failure occurs, the evidence of whatever the failure mechanism, the erosion, corrosion, fatigue, the overload, you can look at each one of these components and see what mechanism has influenced the failure of this seal. When any one of those 5 components begins to break down because of a failure mechanism, we have a seal leak, we have a failure. And again, the industry considers the mechanical seal the original condition monitoring device because it is the weakest link in the chain. It's the fuse in the system. So there could be something related to the pump that's alignment, balancing, some kind of issue that's a forcing factor for introducing those failure mechanisms. It could be an overload or fatigue failure because you have pipe stress, or you have a non-concentric machine where parts are not aligned, or they're not concentric to one another. all of these things come into play and can be determined through your post-mortem failure analysis. And that's where your fracas loop, that failure reporting analysis and corrective actions system comes into place. And so, that's the final loop to make sure, the plan, do, check, and adjust, comes in. And so really failure analysis is critical to measuring and improving the performance of your system.
So before we wrap things up, is there anything else you want to share with our listeners and viewers? Any final thoughts?
Well, I think one thing that just came to mind, when it comes down to those basic practices. So this may sound overwhelming, but it's simple. It's applying basic technologies that you're already using to look at not only your pump, but that seal component. So you're refocusing the same technologies, the same people that you have going out and taking data on bearings for vibration, for example. A bearing you may not alarm on a bearing until, 0.2 inches per second or so many G's of acceleration. But on a seal system, that is the seal is going to fail sooner than the bearing. The bearings a lot of times can handle the misalignment or the pipe strain a lot longer than the mechanical seal. So there's an influence to that. There's also known standards. So a good place to start when it comes down to deciding what the best maintenance practice is, just like we already start with a pump and we say there's already a known maintenance plan for a pump. We want alignment to this standard. We want balancing to this standard. We want torquing to this standard. We want a foundation condition to a certain standard. All of those things come into play. Pipe strain, we want to a certain standard. Those are where we come back into those three. Do we have a procedure? You have to have a procedure. And then is it being followed? And if it's being followed, is it doing what we expected it to do? The same thing comes into mechanical seals, and your partner, your greatest resource in all this is your seal manufacturer, your seal distributor. Those are the ones that are partners in this with you, and we need to utilize those. I think having worked on both sides from a end user to a support consultant to now products, I see a disconnect between those. And a lot of times we'll spend money to hire a consultant to help bridge that gap between the end user and the manufacturer. And the consultant is doing nothing more than listening to both sides and mediating. And that just drives cost. I mean, it's still an important function. I spent a lot of time doing that and enjoyed that process, but those already exist. And both of these two can work together to implement this process fairly easy.
Thank you so much for speaking with us today. We really appreciate you sharing your time and your expertise.
Thanks, Tom.
Thanks to Chris Tyndall for speaking with us today and teaching us all about condition-based maintenance. And huge thanks, of course, to SEPCO for sponsoring this episode. If you're listening to the podcast and would like to watch it, head over to the Pumps and Systems YouTube page to view the full video version. That's going to do it for today. Thank you so much for listening or watching, and we will see you next time.